Hello and welcome back to the lecture of time series econometrics. In this lecture, we are going to actually plot the autocorrelation function for the ARMA model. And we will be using the mathematical deduction that we got in the previous lecture, and we'll be using R to actually plot that, and we'll try to get some intuitive logic as in how the model behaves the way it behaves. Now, if you remember, so in generic term, we can express the successive gamma values in this manner. So, gamma k is equal to phi gamma k minus 1, where the phi is basically the coefficient for the AR component of the ARMA model. Now, here I had a condition that k has to be greater than or equal to 2, because at k equal to 0 and k equal to 1, the corresponding gamma had a very specific value. Now, if I just substitute the value of k for k greater than 2, I will have, say, k equal to 2, I will have gamma 1, and gamma 3, I will have gamma 2, which means phi square gamma 1, and similarly my gamma 4 will be phi gamma 3, which is nothing but phi cube gamma 1, and so on. So basically you can express it as, say, gamma for gamma of like k phi k minus 1 gamma 1, right? And you get the gamma 1 value by solving the corresponding gamma values for k equal to 0 and k equal to 1. Now, so with this form, so what you see is, since my phi is actually less than 1, so for the successive term for the covariance and corresponding the correlation coefficient, autocorrelation coefficient, which is rho, we are actually going to see a decline. So, which means my ACF plot for the ARMA model is going to be exactly similar to the ACF plot for AR model, where we see basically exponential decline for the ACF plot, right, with the increase of the lag. Alright, so that's the theoretical part, and now we are actually going to see with R coding how that actually appears. Now, if we will be using the generic function ARMA ACF for this, and we'll be sort of putting different values for the for theta and phi, and we'll try to make a sense of how theta and phi are actually influencing the graph for the ACF. Okay, so let us begin. Let us name a model equal to M, and all we need here is the value of theta and phi. We don't need the value of sigma square, sigma error square, because that is already cancelled out when we divided the covariance term with the variance term. So putting the, let's say first we put AR equal to 0.2 and MA equal to 0.9. So my value for phi is quite low, quite less than as compared to the value of theta. Okay, so let us just run this and let's see what happens. We see that it looks like a very low order AR, probably since it's a ACF plot, so it probably I would interpret perhaps it's a MA model of say order 3 or something. Okay, so I'm not quite sure. So now let's see, let's increase the value of AR and decrease the value of MA, and let's see how it looks like. So it is going to look like, oh, that's pretty much like a prominent AR model of order 1 or higher order, but it's quite obviously it's an AR model. Okay, and that makes sense because my phi is pretty higher than the coefficient for the MA component, which is theta. So perhaps the impact of the AR component is much higher than the impact of MA component in the model. Now let's see, I put kind of equal value for theta and phi, and let's see what happens here. So I see that automatically the impact of MA has kind of increased probably, because I now have, since it's the ACF plot, it might also be a MA model of higher order, like maybe order 4, 5. But yeah, it could equally be a AR model. So quite obviously, you can see as the value of theta is increasing, the influence of MA component is also increasing. Okay, Nice. So now let us see. Let us put negative values for AR as well as for MA. Now let us make a guess how it should behave. So the moment you put a negative value for the component AR component, it should sort of give you equal exponential decay on the both side of the x-axis, right? So let's see how it works. And quite obviously, it works the way we thought of. We also put MA value, which is negative here, right? So which is this, which is negative here. Now let's see if I sort of in reverse the sign of the MA. So ideally it should work in a way that MA is kind of, contradicting the direction of AR, right? So let's see, then ideally it should probably show some influence of MA in a negative way, right? So let's see how it is. And it is actually, you see the impact of AR has declined. The coefficient values for the successive lags are actually decreasing. So that makes sense. Now here I increase it further. So that means the curve should sort of the height of the different bars should decrease further, right? So let's see if that is the case. It is the case. So our intuition around the value of theta and phi and their impact on the ACF plot is in the right direction. Now let us take the next case that I have written down here. So here we will have the value for theta and phi both pretty high but both negative. So the values are zero point 0.9, minus 0.9, minus 0.9. Now, if I plot them, so intuitively we can expect that it will look like an exponential decay because the phi coefficient is pretty high, and since it is negative, the exponential decay should be around both sides of the x-axis. Now, since the MA coefficient is equally very high and negative, so that should reinforce the impact of the phi coefficient. So that means the height of the bars will increase and they will be on the both side of the x-axis. So let us run that, and that's precisely what is happening. So basically, intuitively, what we are thinking is we are thinking in the right direction, and this kind of gives us an idea about how the ACF plot for the ARMA would look like. So in the next lectures, we will see how we are going to determine the order of ARMA series, the order of AR and MA in ARMA series. So that's something we'll discuss later. But in this lecture, we simply got an idea about how the coefficients are actually determining the ACF, the nature of the ACF plot.